Hello everybody, welcome to our video solution to problem 3 from Superquiz 3. In this problem, we're going to be really looking at the definitions for the unit, or I should say a unit in a ring, and a zero divisor in a ring. So we're assuming here that we have some ring with identity, right? And that's all we know, right? Just some ring with identity. Yeah, maybe it's the complex numbers, but maybe it's just like a matrix ring, or maybe it's modular integers, z mod 6z, who knows? But it should have an identity. And we're asked to criticize and correct the definitions given below for unit and zero divisors of this ring. So let's jump into the first one. So we're going to look at what it means to be a unit, and the proposed definition is that it's an element in the ring with norm 1. Now, what you might be thinking about is many of the examples that we've talked about in class where we were able to define a norm map on the ring. So usually this comes in the form of what we would write as like an absolute value. So we would have the absolute value of an integer or the absolute value of a Gaussian integer, right? Which, well, if we put a square on it, then that's what we actually defined as the norm in this ring. So that was a squared plus b squared. You could put a square here if you wanted to define, what we might reasonably call the norm for an element in Z. Okay, and we've seen this in a lot of other places. In particular, we had like the Dedekind integers, right, where we defined a norm map, and it's all actually in all of these cases, it was just really the distance, right, between the object and 0. Well, then you square that distance. So in the Dedekind integers, this was a squared plus 5b squared. And in all of these cases, an element is a unit if and only if it has norm 1. So this is not an outrageous definition for a unit because we have a lot of examples where this is a true statement. The reason why it's not going to work as a generic definition is because we don't have, for an arbitrary ring, a generic definition of the norm. If we're working, say, with the matrices, maybe you could define a norm map on them, but if you can, it's certainly not going to look exactly like the ones that we've been using for all of these subsets of the complex numbers. So this isn't going to work as a definition based at least on the information we already have. So a better definition for us is one that we gave in class, which is a unit is an invertible element. All right, so i.e. U in R is a unit if and only if there exists some V in R such that UV and VU are both equal to 1. I write it in both ways here because I didn't assume that the ring was commutative, so in principle we should check both directions. Now it's okay to write a 1 here because we did assume that the ring had an identity. So this would be a better definition for a unit, right? Namely that it's an invertible element. All right, let's check out zero divisor. So it says here a zero divisor in our ring R is an element x in R such that x times y is 0 for some y in R. Now, after what I said about unit and the non-commutativity possibility of the ring, you might say, well, don't you really need it to work in both ways? And the way we've defined zero divisor, this would be just fine having it in just one direction. The real problem here is that if this was our definition of zero divisor, then every element in the ring would be a zero divisor. Why? Well, this says you just need to find one element It's just any old element in R that you can multiply by x and get 0. And of course, we've proved before that if you multiply any element in the ring by 0 itself, then you get 0. So in order for this to be a reasonable definition of a zero divisor, we need to assume that the y you find is not equal to the 0 element. That way you legitimately have x times some non-zero element equaling 0. That's actually what we want. Again, in the sense of does x divide 0, that's always true because you can write this down. But it's not really a useful way to define things because everything would be a zero divisor in that case. All right, and we're trying to isolate those things, which really you can multiply ultimately two non-zero things. All right, I mean 0 we do treat as a zero divisor, but we ultimately want to be able to look for things where you have two non-zero entries or elements whose product is 0, thus showing that your ring wouldn't be an integral domain. Okay, so hopefully this helps clarify some of these definitions. Next video, we'll go into some examples of units and zero divisors.